So first, I would like to thank the organizer for the invitation to this workshop. I'm going to talk about elastic instabilities and turbulence, even though I'm not sure that I'm still authorized to use this word now, in a viscoelastic system which are called giant micelles. Elastic turbulence is also named turbulence at low Reynolds number, or turbulence without inertia. And so it's a phenomenon which is well known to develop in a dilute and semi-dilute solution of long chain polymers. So in flows of dilute and semi-dilute solution of long chain polymers with barely any initial forces, and it is driven by elastic forces. So it's a phenomenon which has been extensively studied by Steinberg Group at the Weizmann Institute, and so they were the first to observe flows with power law structures, so very reminiscent of inertial turbulence, but with a negligible inertia in that case. There are still a fundamental question behind the understanding of this phenomenon, but there are also many applied and industrial challenges. And so indeed, elastic instabilities and turbulence are one of the main production limiting factor in polymer processing, such for example in extrusion. So when a polymer solution or a polymer melt flows out from a tube, and elastic instability and turbulence are likely to generate this very irregular flow pattern of the outflows, and so they are clearly to be avoided in many applications. But on the other hand, elastic instability and turbulence could be useful at a very small scale to create effective mixing and heat transfer. So at very small scale, so for example in microfluidic applications where inertia is completely absent. There might be, but I'll let the audience decide, there might be another interest in studying this kind of phenomena. So indeed, the flow behavior of a dilute polymer solution, for example, is essentially this one. So this system have a constant viscosity and elastic stresses. And so this kind of behavior is well captured by a purely elastic Dumble model. So this means that you can model the polymer molecules as two beads separated by a spring, and purely elastic spring. And it turns out that this model is linearly unstable in flows with curved streamline. So with respect to radial velocity perturbation. And so the base mechanism of this instability is the following one. So, as a result of a radial velocity perturbation, the Dumble will be deflected and stretched by the base flow. So this will lead to an extra tension along the streamlines, which in turn generate a radial pressure disturbance that finally amplifies the initial perturbation. So this is the base mechanism for the purely elastic instability. And in 2003, Ogilvy and Proctors drew an analogy between the purely elastic instability and the magneto-rotational instability. And so Hantaoji gives a nice talk about that on Tuesday. And so so the idea is that so there is this kind of analogy, or sketch here, and with this mechanical model here, and so the magneto-rotational instability was discovered by Balbus, and so it is likely to drive the angular momentum transport in accretion disks. So in that case. That are the magnetic forces that act as a spring under tension between two fluid elements. And using this analogy, Ogilvy and Proctors establish a mapping between the equation of the purely viscoelastic Dumble model and the MHD equations with some hypotheses that have been recently relaxed by Mutabazi and co-workers. And using the same analogy, Fuxon and Lebedev were able to predict, so to make some prediction about the turbulent state, in particular regarding the velocity spectra, so the spectra of the velocity fluctuation. So they found power law decays with exponent smaller than -3. Okay, so So the idea is that maybe, I don't know, but maybe the study of this kind of fluid can be useful regarding some aspect of MRI. Okay, so so in the following, I will recall some generalities about viscoelastic fluids, and also about the analogy between the purely inertial and the purely elastic instability in Taylor-Couette flow. And then I will show you the phenomenology we have observed in a viscoelastic system, which is different from regular polymers, and which are the giant micelles. So just a few words about viscoelastic fluid. So one way to define a complex fluid is to look at the length scale and time scale involved in the system. So a simple fluid like water is as a structure, so is structured at the molecular scale, so typically 0.1 nanometer, and the corresponding time scale are associated with the molecular rearrangement, and they are in the order of the picosecond typically. So in contrast, viscoelastic fluids, as many other complex fluids, are structured at a mesoscopic scale, so typically ranging between 10 and 100 nanometer. And so the existence of such mesoscale or mesostructures provides additional degrees of freedom in the system. And the characteristic time scale associated with these degrees of freedom is much larger, and they are typically ranging between 10⁻³ and 10 seconds. And so such order of magnitude of the characteristic time scale makes the system easy to probe or easy to excite with a shear flow or with usual shear flow or usual flow rate. And so the idea, so here is a sketch of a simple shear flow. So the idea is that for a sufficiently high shear rate, the flow will modify the mesostructure of the system, which in turn can feed back on the flow itself. And so typically, for applied shear rates larger than 1 over the characteristic time of the system, the structure is modified. And so in particular, for sufficiently high shear rate, the dumbbells, which model these polymer molecules, are deflected and stretched. So the shear rate, so the shear makes the system, and so the fluid anisotropic. And for most polymer solution on melts, the most important effect is the buildup of a difference between the normal stresses that exert along the flow direction and in the flow gradient direction. So there is a buildup of a first normal stress difference here, and so which gives rise to elastic forces that drives the instability. Okay, and so here is a spectacular manifestation. So it's one of the most spectacular manifestation of the existence of elastic stresses. So this is the so-called rod climbing effect or Weissenberg effect. And so we have a short movie here due to evil group. So in flows with curved streamlines, the stretch polymer pushes inward, so it generates a centripetal pressure gradient that drives the fluid inward along the rotating rod. And this is in contrast with what happened for a simple fluid, where the pressure gradient pushes the fluid outward. Okay. So I just want to spend a few minutes recalling some features of the purely inertial instability and purely elastic instability in Taylor-Couette flow, just to show you the analogy. So the Taylor-Couette flow is the flow between two concentric cylinders, and in the general case, the two cylinders can rotate independently. So let's start with the purely inertial case. So for Newtonian fluid, so the flow dynamics is governed by the Reynolds number, so which compares the inertial and viscous forces, and which can also be written as the product between the shear rate and the viscous diffusion time. And as the Reynolds number increases, the flow is likely to become unstable, and there can observe a sequence of bifurcation from a laminar base flow to non-trivial coherent flow, and ultimately to turbulent flows. In the case of the flow with curved streamline, so in the Taylor-Couette flow, so Taylor, in his seminal study in 1923, determined experimentally and predicted using the linear stability analysis of the momentum equation. So he was able to determine the stability boundary here between the base quake flow and the first mode, which is a Taylor vortex flow here. And so both in the counter-rotation and the co-rotation region of the flow diagrams. And so he shows that, for example, in the small gap limit and where only the inner cylinder is rotating, so which corresponds to this red line here, the relevant dimensionless number that drives the instability is the Taylor number, which involves the Reynolds number and the curvature ratio, so the ratio between the gap size and the inner radius. And so typically for a Taylor number larger than 41, so the flow evolves toward a Taylor vortex flow where vortices are stacked along the vortice direction and whose sides scale as the gap size. And if you increase the Reynolds number, you are likely to observe a richness of flow pattern as illustrated on this famous diagram by Anderegg, Sweeney, and Golub, so both in the counter-rotation and co-rotation domain. So now, if we look at the purely initial case, so approximately 70 years after Taylor, Larson and co-workers, so by mirroring Taylor's seminal study, have shown that the flow of a polymer solution, so an elastic solution, is likely to become unstable, even when the Reynolds number is 0. Okay, and so they show experimentally, and they perform the full linear stability analysis of the Dumble model, which is, so the equation is given here, and so they observe that the flow is likely to become unstable above a critical threshold, which involves the curve, still the curvature ratio, and another dimensionless number, which is the Weissenberg number. And the Weissenberg number compares elastic forces and viscous forces, and it is defined as the product between the shear rate and the relaxation time of the system. So in that case, the nonlinearity does not come from the momentum equation, which reduces to the creep flow equation here, but it comes from the equation of evolution of the stress tensor. And so typically for Taylor number larger than 1, the Taylor quake flow of an elastic solution is likely to become unstable. And again, if we increase the Weissenberg number, we expect to observe a cascade of instability. So in some cases, it's possible to leap over this cascade and to go directly from the laminar state to a disordered flow state, which is called a turbulent flow state here. And so all those pictures come from, so the plot come from Steinberg works. So the transition from the laminar state to the disordered flow state is so it's characterized by an increase of the flow resistance, and it is hysteretic. And in addition, the velocity fluctuations exhibit power spectra with polar decay, with exponents that seems to depend on the flow geometry. So in particular, in von Karman swirling flow, so in the flow between two disks, they were systematically found smaller than -3, while in the Taylor quake flow, they range between -2 and -1. Okay, so this was so all I described here is for the purely elastic case, and but the parameter space is huge. So as illustrated on this diagram here. So here I have extended the Newtonian plane explored by Anderegg and Sweeney and many others by adding an axis which stands for the elasticity number. So this is the ratio between the Weissenberg number and the Reynolds number. And so depending on the interplay between elasticity and inertia, you can expect different flow regime where they will compete. Okay, so this is the purely elastic case. But you can expect so different flow regimes, so different route towards the disordered flow, and disordered flow with different statistical properties depending on the position here. So my gram told you about this regime here in a tube, I think, on Monday. Okay, so until recently, this kind of instability and elastic turbulence were only explored in polymer solution, and we have uncovered the same kind of behavior in a different kind of viscoelastic systems, so in different class of viscoelastic systems, so which are called giant micelles. So what are giant micelles? So this system looks like elongated and flexible cylinders, which result from the self-assembly of surfactant molecules. So surfactant molecules have a polar hydrophilic head and an hydrophobic tail. And so they self-assemble to form aggregates of different morphology, and giant micelles correspond to cylindrical morphology. And so in most cases, so in a large range of concentration, they exhibit a single relaxation time. And in contrast to polymers, they have the ability to break and recombine continuously under the effect of the temperature. So that makes them insensitive to irreversible mechanical degradation, especially in disordered flow regime.
Are they entropically coiled?
So no, that's a difference. So I can.
Like an elastic fiber?
Yeah, exactly. But this so as you will see, they exhibit elasticity, especially when they become entangled, right? And so they exhibit a very rich nonlinear behavior depending on the concentration range. So in the dilute regime, where there is no interaction between the micelles, the flow behavior is the following one. So it exhibits some shear thickening, so which means that in some range of shear rates, the viscosity of the system increases. And this is just due to a change of the mesostructure in the system. So I'll come back on this.
You've drawn that as a sharp onset.
Yeah.
It is. Okay.
Yeah, it is. And in the semi-dilute regime, so where they are entangled, there are two types of behavior. So the most standard behavior is shear banding. So this corresponds to shear localization effect. So I will explain this in the next slide. And they can also exhibit shear thinning. So just the viscosity of the system decreases by increasing the shear rate. Okay, so just very briefly, a few words about.
Just one question.
Yeah.
So this single relaxation time behavior,
Yeah.
if I remember right, it takes place in some part of parameter space, but not.
Yeah, it's so all the semi-dilute.
Time versus
all the semi-dilute micelles exhibit a single relaxation time. In this range here, it's not the case. You have spectrum of relaxation time. But so yeah, but here you have a transition, and the transition is from this state to this kind of state. Yeah. Okay. So just a few words about the tools we have used to explore this system. So I will skip the details. So the only idea to keep in mind is that we are able to image the flow in a radial plane here, so using laser sheet or white light, whatever. And we are also able to image so a velocity map in that plane using ultrasonic velocimetry experiments, so which gives us the base flow as a function of r, z, and time. Okay, so let's start with the first example. So I start with a shear banding giant micelle. So in that case, the Reynolds number is typically 10 minus 4. So the elasticity number is much larger than 1, so we are in the purely elastic range. So here is the shear stress response of the system as a function of the shear rate. So the shear stress is composed of two increasing branches separated by a stress plateau which extend between two critical shear rates. So a simple picture of that is just so there is similarities with the liquid-vapor transition at equilibrium, so you can think of that to understand what happened here. So the two branches here correspond to two different states of the system. Along the low shear rate branch, the micelles are entangled or strongly disordered, and along the high shear rate branch, they are strongly aligned along the flow direction. So if we apply a shear rate along the low shear rate branch, we observe that the velocity field is linear, as expected for a Newtonian fluid. And if we look at the system between cross polarizer, we observe nothing special. Now, above the first critical shear rate, the flow becomes unstable, and it evolves toward a banded state where two shear bands, so two bands of differing viscosities and different shear rates, coexist at constant stress. And the high shear rate band is birefringent. So if we increase the shear rate, we just change the relative proportion of each band according to a simple lever rule. And finally, if we reach the end of the stress plateau, so the induced phase, which is strongly aligned, fills the wall gap of the Taylor quad device. And the flow is homogeneous again. Okay, so this is a system where we have shear localization effect, which is something which is ubiquitous in complex fluids. So now let's look at the radial plane. So if we look at what happened along the low shear rate branch, we observe nothing special. So this is the view of the gap of the Taylor quad device, right? So now, here is a short movie that illustrates what happened if I share the system at a constant shear rate along the stress plateau. So the left-hand side corresponds to the inner rotating cylinder, and the right-hand side corresponds to the fixed outer cylinder. So at constant shear rate, we have the formation of the bonding structure. So the high shear rate bond is bright here, just because it's slightly scattered, if it scatters light. And the low shear rate bond is here. And as time evolves, you can observe that the interface between the two bonds undulates along the vorticity direction. So I can play the movie again, but using white light. In that case, we lost the contrast between the two bonds, but we are able to image the interface here. And so what we observe in that case, after some time, so the interface at constant shear rate is initially flat between the two bonds. And as it starts undulating, concomitantly, we can observe the development of Taylor-like vortices, which are located in this high shear rate band. So this is this band which is unstable, okay? And so the flow dynamics is well reflected by the velocity field. So this is a time series of the velocity map, and we observe that the flow is modulated along the vertical direction. So if we now increase the shear rate along the stress plateau, we change the proportion of the high shear rate band, and we observe different flow dynamics. So here we have annihilation of pair of vortices here, and creation of pair of vortices somewhere else in the gap of the Taylor-Quad device. So a pair of vortices is going to appear right there. If we keep increasing the shear rate up to the extremity of the stress plateau, this high shear rate phase fills the whole gap of the Taylor-Quad device, and the flow is laminar again. Here I have summarized the spatiotemporal dynamics we have observed along the plateau here. So it just consists in plotting the interface profile in gray level as a function of the z coordinate and the time, and we observe a zigzag pattern, then a pattern of creation and annihilation of pair of vortices, a stationary pattern, and again a pattern of creation and annihilation of pair of vortices, but which is opposite to the first one. And so we can obtain quantitative information using the velocity field, and we can also draw follow the flow dynamics using the velocity maps gathered as a function of time. Now, if we keep increasing the shear rate along the high shear rate branch, we observe this kind of behavior. So the flow seems completely disordered. So we have an additional transition in that case, and we have huge fluctuation of the intensity scattered by the sample. And so this is a disordered flow state, and the corresponding spatiotemporal dynamics of the velocity field is given on this diagram here. Okay, so if we look a bit more at this transition here, so between the laminar flow state and the disordered flow state or turbulent flow state, we observe that the transition is hysteretic. And so in the transition range, we have some kind of B-stability. So in the shear stress time series, so this corresponds to the laminar state, this corresponds to the disordered flow state, and we have in the transition range some kind of excursion of the shear stress between the two states. And we also observe that the turbulent fraction is directly proportional to the shear stress. So we have tried to quantify a bit more this disordered flow state, and we found that the PDF of the energetic power is not Gaussian, that is positively skewed in that case, and we try to compute the velocity spectra, so the intensity fluctuation and velocity fluctuation spectrum. And so in both cases, we observe power law decays. So I don't know if I have sufficient decay here to conclude, but so the exponents are different from what has been observed in polymer solution in Taylor-Quad device. Something which is a bit striking too, and maybe somebody in the audience could have an idea. So we do not find the same exponents in the frequency range and the wave vector domain. And so it means that either the Taylor hypothesis is not valid or that the disordered flow state is not isotropic. I don't know. If someone has an idea, I will be happy to take it. So all these features are strongly reminiscent of what has been observed for polymer solution, even if there are some differences. So I don't know if I can qualify this disordered flow state as turbulent flow state, elastically turbulent flow state, but it strongly looks like this. Just to finish on that particular case, in the purely elastic range, I can show you a slightly different situation. So So in that case, the route towards the disordered flow state is a bit different. So I'm sorry, there are many bubbles in the system here, but if you look at the motion of the bubbles, we can observe that the flow is strongly elastic. So in that case, the transition toward the turbulent flow state happens right across the bending regime. So you can observe this turbulent burst that disrupt the high shear rate band. So the route towards the disordered flow state is a bit different in that case. Okay, so let's turn to the case of purely shear thinning giant micelles. So you can go continuously from shear bending to shear thinning just by decreasing the surfactant concentration. And so we finally end up with this blue curve here, so which is purely shear thinning. And so when we ramp the shear rate up and down, we observe no hysteresis in that case. And if we follow the flow pattern using this kind of protocol, we observe the same pattern by increasing and decreasing the shear rate. So in that case, we have a transition from the base quad flow to standing vortices for Weissenberg around 76. And then we have disordered flow state here. And if we compute the elastic Taylor number or the inertial Taylor number at the first transition here, we observe that they have the same value. Yeah. Yeah.
It was dilute case before you showed before, or dense case without it?
So the previous case or this one?
Previous case.
So the previous case. So the picture is right there. So it's a midi-dilute. Okay. It's a case where the micelles.
Okay.
So we are semi-dilute and we are semi-dilute. Okay. The previous case we are still semi-dilute here, but so the mesh size of the network is larger. Okay. But we are still semi-dilute here. Okay. So we have still entanglement in that case. And so what we observe is that at the first transition, the elastic Taylor number and the inertial Taylor number have the same value. So this means that the elasticity number is close to 1 for this kind of system. And so it means that what we observe here is not a purely elastic disordered flow state, but it is an elastically dominated turbulent state. And so this is something which has also been observed by Müller recently. And so we try to compute the velocity, so the spectra of the velocity fluctuations. And in contrast to the previous case, we have something which is not featureless because we have these broad peaks here. So we have a structure here in time and space, which stay in the system. And so, yeah, it's a situation very, very similar to what happened for regular polymers. At moderate elasticity, so typically, let's say for polymers, its elasticity number is 0.1 or 0.2. Okay, so now if I go to the dilute case, so this is this case here. So basically, the viscosity of the system in that case is the viscosity of water. Okay, and what happened for this kind of system, if you increase the shear rate, is that you observe a jump in the viscosity, and so during this jump, you have the buildup of a new structure. So what happened is that the morphology of the micelles does not change, but they grow in size until they get entangled. Okay, they get slightly entangled, but sufficiently to generate elasticity. And an important point also is that when you share the system in this region here, so in this viscosity jump, you need an induction time to generate, so to build up the new elastic phase. So I just want to illustrate this case with two different shear rates. So this is the same sample at 2 different temperatures. And so we apply a constant shear rate and we observe as a function of time what happened. So here is the first case. So this is the velocity map in the radial plane. This is the spatiotemporal dynamics, which is built from the value of the velocity at mid-gap. These are velocity profile at different height along the z direction. This is the shear stress. The shear stress recorded as function of time in the same time. And here, this is the slip velocity measured at the inner wall. And so when you share this system, so initially the velocity profile is linear, and so you have nothing special in the spatiotemporal dynamics. But once the shear-induced structure builds up, the elasticity in the system increases, and the flow is destabilized, and we end up with this disordered flow state here. So, and you can see that the shape of the profile is completely changed in this region here. So we started with a system with no elasticity, so the Reynolds number is large, and the elasticity number is 0. And we end up with a final disordered flow state where elasticity dominates. The other case is a bit more complex. In that case, at the very beginning, so the flow is homogeneous, and then we have this first instability. And if you compute the Reynolds number, so the Taylor number here, so it's larger than 41, and so this structure here is purely inertial. But after the induction time, when the shear-induced structure builds up, this Taylor vortex flow is completely modified due to the elastic forces, and we end up again with a strongly disordered flow state. So we did the statistical properties of this disordered flow state remains completely to be characterized. So for the moment, we have not at all studied the properties of this case, but we know that so by just computing the dimensionless number, we know that we end up with a state where the elasticity number is larger than 1, and we have competition between inertia and elasticity, but elasticity dominates. Okay, so I can conclude. So I try to show you that elastic instabilities and turbulence can develop in another class of viscoelastic systems, which are giant micelles, which are different from regular polymer. And the disordered flow state can be observed in a large range of elasticity numbers. It's not only purely elastic. So this system may be an alternative to regular polymers to study the statistical properties, in particular because they are insensitive to irreversible mechanical degradation, which is a real problem with polymer solutions. They exhibit a complex nonlinear behavior, so they cannot be bundled by the simple Dumble model, but so exhibit a shear localization effect or shear thickening, which are connected to the development of a new mesostructure with enhanced elastic properties. And this new structure, the emergence of this new elastic structure, which are responsible for the instabilities and the turbulence in this system. So yeah, the big question is, what are the underlying mechanisms? So comes back to your question at the very beginning. So for the elastic turbulence, there is no elastic counterpart to the cascade picture in inertial turbulence. And so sometimes the cold stretch transition is used to explain some phenomena in elastic turbulence, such as intermittency and energy transfer. But the problem is that, there is no cold state in giant micelles. So the cold stretch transition is unlikely to develop in that case. Okay, so I just mentioned at the end that there were some wall slip in the turbulent state, and this is something which is ubiquitous in this system, whatever the concentration range. We systematically observe large wall slip when the disordered flow state develop, whatever the concentration range. Okay, so I didn't talk about, so I talked only about N1, but there is also a second normal stress difference in the system, which is likely to stabilize the flow, and so we may wonder whether we can derive, for example, a general instability criterion, which includes the role of N2. There is a question about the dependence on the flow geometry. So I showed in a previous slide using data by the Steinberg group that the statistical properties are different in Taylor-Quade flow or in von Karman-Swirling flow. So the data in Taylor-Quade flow are rather scarce, and so it would be interesting to systematically study the dependence on the flow geometry of the statistical properties. So just to come back to the initial motivations, So I don't know, maybe this system could be used to give some insight of phenomena that happen at very large scale, for example, by studying this kind of instability in the Keplerian regime. So I don't know if it could be interesting. And another question regarding the applied challenges is to find a way to control these instabilities. The idea we have for the future is to try to control it using the boundary conditions. So just to play with the boundary condition, the roughness, the softness, just to see if the fluid structure interaction can modify the threshold. Okay, so I'm out of time. So just would like to thank all the people who contributed to these works over the past years, and you for your attention. And yeah, I'm done here. Thank you.
Okay, so yeah, please.
No.
I think it must be done. Because that, so when you cite, it's good to cite Lumley because he asked this question in 70s and he was really kind of contributing this thing very much. So there are lots of questions here. There must be close stretch transition because you are telling that there is single single relaxation time. So when something must happen. Then if you consider dilute case, polymer elastic turbulence is single molecule phenomenon. So you can understand it starting from one polymer.
Yeah, but in our case, in the dilute case, you have nothing. So to have something, you have to trigger the transition towards the entangles. So we take advantage of this transition. So we start with something which is dilute with no interaction, and there is a change of the mesostructure of the system which starts to entangle. And in that case, you can build up elastic stresses. So we will never observe in this kind of system the same kind of transition as that has been the one that has been observed in polymer. In the purely dilute case, because we need a change of morphology, but of change in the network to generate elasticity and then to trigger the instability.
Yes, so I'll tell the most relevant thing. So for polymer solutions, you have okay.
I have one. Okay.
Yeah.
So on your point though, I'm curious about what happens in these kinds of solutions in cross-channel flows.
So yeah, so in cross-channel, Simon Howard did a lot of things on that, and there are also instabilities. So we have asymmetry of the flow, but he used it. So he didn't try on this dilute system. He tried on the semi-dilute, which exhibits shear banding, right? And so yeah, so he did a lot of So I skipped the question. Sorry, excuse me.
No, that's fine. I was, there are these beautiful experiments of Paulo and Jerry Dolan.
Yeah.
Right.
Yeah.
So it sounds like there's analogies to these kind of symmetry breaking.
Exactly. They exhibit the same kind of symmetry breaking. Yeah.
Okay, other questions? Yeah.
I didn't understand one thing. In this here, as a function of shear rate, you're going from something that looks dilute to something that looks entangled?
Yeah,
what is the mechanism?
It's unclear, but the idea is that you have some collision between the micelles and
somehow you're
promoting the elongation. So it has been shown using neutron scattering. So you can clearly observe growth in length of the micelles, and then finally, so if you shake the sample, you clearly observe. Yeah, it's not a gel, but it's strongly elastic, and so you have recoil and. So you generate the elasticity by this transition. So
you somehow promote joining
by
shearing in some regime. Right?
Yeah.
But there's no kinetic model of this, or there is, or
no, not really. So Cates tried to do something like this, but he used a ring-like structure, and so they are not likely to develop in this. So they have not been observed in this system so far. So.
Okay, I think we run out of time. I will keep my question in the discussion part.
Yeah, sorry.
Okay, let's thank the speaker again.
Okay. So I'm pinch hitting for somebody. So yeah, just put this together on the fly. So I hope I'm cogent and coherent. I'm going to be talking about, as the title says, geophysical turbulence. So you can think of this as a follow-on to Oliver Bullo's talk yesterday, and also I have material here that you can think of it as an extension to Rohit's nice talk yesterday. So mainly the application that I've been thinking about lately is for exoplanets and neutron stars, flows on the surface of neutron stars. But let's see. So what you're looking at is the in the business of geophysical fluid dynamics called the primitive equations. This is the essentially Navier-Stokes on whatever geometry that you care to study. If you're trying to study climates and so forth, it's usually written down in spherical coordinates. And the thing to note here is this last equation, which is, of course, the hydrostatic balance. So immediately we're talking about large-scale, small aspect ratio structures. Right? What makes this talk sort of geophysical is that at least for the Earth and all the planets in the solar system, in the momentum equation, the pressure gradient is very well balanced by the Coriolis term here, right? And then the ageostrophic part just means flows in which the balance isn't so good, okay? Now, usually, if you try to solve the primitive equations, it's horrendous. There are no general solutions known. And even trying to solve the equations numerically is a nightmare. So if you're interested in studying things like mechanisms in particular, you might want to try and rationally reduce the primitive equations. And this is one rationalization. You assume the flow can be decomposed into a vertical and horizontal part, and vertically integrate the primitive equation that I just showed you. And what you can wind up is a set of 4 equations, one for the horizontal winds, and one that's sort of a temperature or pressure-like term, and this is the equation for entropy, if you will. So what this describes is a single layer of fluid that has variable depth, either by undulating surface or both undulating surface and bottom. The former case makes the single layer a homogeneous layer, homogeneous density layer. The second case makes it inhomogeneous. So if you're dealing with flows that have markedly different temperatures from one location to the other, you have to use the second set of equations. The first set of equations is a very well-known set of equations in geophysical fluid dynamics called the shallow water equation. Okay, so you can think of that as the homogeneous shallow water and this inhomogeneous shallow water.
James,
Yes.
is kappa some coefficient of thermal expansions?
Oh, sorry. So kappa is the gas constant. So it's for ideal gas, it's 2/7 for diatomic gases. The A naught is sort of vertical shear factor, which you can set to 1 for most purposes. Anything else that I need to explain? This is, in normal shallow water, this will be like the height term, and this will be like the bottom boundary term. All these are just whatever your favorite forcing and dissipation. It looks scary, but it isn't. If you set A naught equal to 1 and let kappa go to 1, then it reduces to your shallow water equation. Okay? Yeah. I particularly like it because there's a huge set of machinery already available to solve the shallow water equation, and to solve these set of equations based on using those tools is fairly simple. All right. We all heard about inverse cascade a lot this workshop, so just a demonstration of what inverse cascade means in physical space. You're looking at the so-called potential vorticity. Never mind what that is, just for those of you who don't do GFD, just think of it as a tracer of the fluid. It is a materially conserved quantity. And you're looking at flow on the sphere from top down, looking down from the North Pole. And you're seeing vortices undergo mergers, which signify inverse cascade. And that usually shows up as the centroid of the energy spectrum moving towards the low wave number regime. Okay? This, if you, this happens in principle, whatever rotation rate you have, but I happen to be showing you a picture from a fairly slow rotating sphere. If you turn the rotation off completely and integrate for a long time, what happens is eventually it goes to, long time means many, many, many thousands of eddy turnover times. It goes to a vortical quadrupole, 2 plus 2 minus, and that's one of the only true manifestation of spherical geometry. That is, on the same situation on the plane will form at the end a vortex dipole, a plus and minus. This happens because the first total mode on the sphere corresponds to angular momentum. And angular momentum is a conserved quantity. And if you think like a quantum mechanician, that is a forbidden state. So it doesn't make transition, the energy doesn't make transition to the lowest mode. The next available one is the n equals 2 mode, where n is the total wave number, and that corresponds to the 4 vortex mode. Now, 4 vortices are chaotic. Their motions are chaotic, so once they form, they just kind of revolve around, and you can't predict exactly where each vortex is going to be. Okay, so that's the background. Yesterday, Oliver was talking about geostrophic. So in terms of dynamical parameters, there are, for now, 2 main ones. That's the Rossby number, which is a measure of the vorticity compared to the background rotation. Or if we're talking about planets or stars, the rotation rate of the planet or the star. And then a quantity called the Froude number, which is the analog, our analog of the Mach number. In this case, since we're talking about subsonic speed, so shallow water is derived based on the fact, starting from the fact that the fluid is incompressible. So there's no sound, of course, in that system. However, it permits gravity waves or buoyancy waves. So the Froude number is the ratio of the advection speed to the gravity wave speed. Okay, if you drive the gravity wave hard enough, it will reach up to sonic speed, but not pass. That's the maximum speed that it can get.
Sorry, and
yeah.
Because it's shallow water, the gravity wave speed is just set by the depth.
Yes.
GH kind of thing.
Yes, that's correct. Okay, just in case you forgot, showing you the solar system planets, I'm going to kind of, in this talk, focus on the giant planets only, right? So just remember what they look like. All right. And I want to show you some numerical experiments, much like the ones you saw yesterday. However, yesterday you saw solutions using the non-divergent form of the shallow water equation, if you will. This is fully horizontally divergent shallow water equation. And the experiment you're seeing is using the known observable physical parameters for the giant planets and nothing else, right? Initializing your calculation with small-scale random vorticity, the plus is co-rotating and blue is counter-rotating, so plus and minus signs. And the idea here is to do as little as possible with that experiment, and you just let it go and see what happens. So I'm just showing you two cases, the experiment with Jupiter's radius, Jupiter's rotation rate, Jupiter's equilibrium temperature, surface gravity, and average kinetic energy, all the values of which are observed and well known. And if you do that, the evolution naturally goes to a state in which you're looking at potential vorticity. Not only do you have multiple banding or jetting, right? Those are the alternating tight and relaxed gradients of potential vorticity. Also very coherent vortices embedded within the jets. Okay, if you do the exact same experiment now using Neptune's parameter, remarkably, you get something very close to Neptune. Right? Now I don't want to tell you that this is a perfect model and it predicts everything, but it given that it's such a simple model and all you're doing is putting in observed parameters, it does incredibly well. Okay? In fact, those banding, as I alluded to, corresponds to jets. So what you're looking at is the observed jet pattern on the left column and the corresponding jet pattern coming out of the simple calculations. And it does pretty well. Namely, it gets the jet widths, the rough number of the jets, the amplitudes. But you'll see that the one thing it doesn't seem to quite get, and that is the equatorial jet seems to have reverse sign for Jupiter and Saturn only. It does perfectly fine with Uranus and Neptune. Okay, now we know there's something missing, right?
Can I ask a question?
Yes.
So you're using a shallow water model,
Mm-hmm.
and somehow that fits in with simulating a gas giant?
Yes.
Okay.
In hindsight, if you think about it, it's almost the perfect model to use. I hope I can explain it. If not, maybe it'll come out in the questions. It turns out what's missing is, of course, I haven't forced anything. Right? This is a freely evolving calculation, nor do I have any sort of large-scale dissipation. So if you in particular, we know Jupiter's cloud deck is radiating, it's cooling off, right? Radiating infrared radiation quite efficiently. So if you put that in, it turns out you can naturally get the jet to reverse. Okay? So it gets that too, right? This is quite simple to explain. The radiative cooling, large-scale radiative cooling, acts like a preferential dampener. It tends to damp the higher latitudes more than the equatorial regions. And it's all the meanwhile trying to conserve angular momentum. So if you preferentially damp that, you tend to accelerate the equator. It's a very simple mechanism. Another feature that only shallow water equation will get, and this is, again, predicted before we knew this would exist, is that the number of co-rotating and counter-rotating vortices are different. In fact, when Voyager went to Jupiter and did a vortex census of all the storms on Jupiter, it found that over 90% of the vortices are of anticyclonic kind, so counter-rotating kind. And you can see that here. I'm just showing you the PDF of the vorticity. And actually we just showed sample of simulation. And you see all the axes marked where the symmetry between cyclones and anticyclones are broken. And it's only in that band. Everywhere else, it doesn't break that symmetry. Wow, I don't think I'm going to get to half my time. Right? And the reason for that is has to do with the idea of balanced modes. So I mentioned that in these cases, the pressure gradient is balanced by the Coriolis rotation. And one of the effects of that is to kind of mute the sloshing of the fluid, okay? If you mute the sloshing of the fluid, what happens is the equation will show that there's a Helmholtz operator relationship between the flow and vorticity, from the, between the stream function and vorticity, and that leads to a interaction length between structures. And locally, anticyclones have longer interaction length than cyclones, and therefore they're more coherent. Okay, and that's why the breaking occurs. And that only happens if you allow the sloshing to get larger and larger. Or another way to say that is to reduce the interaction length between structures. I think I've totally run out of time, so I won't get to the hot Jupiter or neutron star part of the talk, but if people are interested, we can, I guess, carry on in the discussion section. Okay. Oh, the boss says I have 5 minutes still for discussion. So if people, now and it jumped to 50 minutes. And do you want me to keep going, or would you like to ask questions, or would you like to hear the talk through the questions? It's up to.
I'd like to see the neutron stars.
At least some MHD things. How about that? I think. Okay, so in 4 minutes or so, I will try to do my best. So let me first, before that, set the stage and get you to think about hot Jupiters. Okay, so we're only talking about Jupiter-like planets because from a modeling standpoint, those are the most sort of ideal planets to think about. You're not screwed by mountains or oceans underneath, right? So if you ask an artist, what do you think a hot Jupiter will look like? You tend to see this almost always. Essentially what it is Jupiter, and then you change the color on Jupiter, right? It turns out these hot Jupiters are, of course, very hot because they're very close to their host star. If you do a thought experiment, and since I hope I convinced you that shallow water does great at modeling gas giant atmospheres, we can do a thought experiment where we bring the planet closer to the sun. In other words, we thicken the shallow layer, right? That corresponds to a hotter equilibrium temperature situation. And if you do that, you start getting things that actually don't quite look like Jupiter, even though everything else is a Jupiter parameter. And the reason is, even though you form jets, multiple jets like on Jupiter, the deformation radius is now increasing. The interaction length is increasing. So even after you form the jets, one jet can see another jet nearby, and they tend to merge. And that's the reason why the alternating gradients are muted, and the jets look very diffuse. Okay, we can keep on going and bring the Jupiter even closer, right? Remember what the artist's rendition was. If you put actual physics into the picture, you actually would see this. Again, potential vorticity seen from the side and from North Pole. And what you get is preferentially cyclonic polar vortices, lots of wave breaking. It's a crazy mess and very turbulent in the middle. You see the effect of the heating, and you see mid-latitude and tropical cyclones. Okay, so I think I'm going to quickly, if Ali were here, but since Boris is here, I'm going to try and show. What's shown here on the right is energy spectrum from one of these very inhomogeneous turbulent calculations, right, with rotation and stratification. And it turns out in this ageostrophic condition, not only do you form vortices and jets, which are very essentially laminar kind of structure, you also form very high amplitude gravity waves, right? And the gravity waves are what you're seeing in essentially this part of the spectrum. If you're not well resolved, if you don't have enough resolution, if your calculation is done poorly, in fact, you lose all this, right? And you'll wind up over dissipating everything else, right? So it's one of the points I would like to make in the talk. And then finally, let me just jump to magnetic case. So here, it's easy to do MHD shallow water calculation. All it really requires is adding a Lorentz term and then the induction equation. Okay. So now you introduce one more parameter, the so-called plasma beta, which is equivalent to the Mach number, but with magnetic field, right? So the reference velocity is now the Alfvén velocity. That's the velocity when you perturb the magnetic field. That's the velocity induced on the magnetic field. Okay, last slide. Remember, in 2D turbulence, you simultaneously conserve, you can show this from the equation, both the energy and entropy, right? The energy inverse cascades, meaning it goes upscale. When you introduce rotation, there's an, roughly speaking, an arrest scale in which the inverse cascade is stopped. It is, at that point, it radiates Rossby waves, or planetary waves, those undulations of the potential vorticity, and the jets are created, okay? Now, that's because of the equation, the properties of the equation. When you add the magnetic field in there, you destroy that those conservation laws. What's now conserved is the magnetic potential, right? Not the, and the energy doesn't inverse cascade, okay? So even though there's rotation, since there's no inverse cascade, the system has nothing to stop, so it cannot create jets, okay? So jets are destroyed, and this is actually, Earth is half a Gauss. So you might think this is quite large, but compared to a neutron star, this is already still 5 orders of magnitude smaller in magnetic field value. And with that, I really should stop. Thank you.
So yeah, I'm James, number 2. And I'm going to be talking to you about this anisotropy that I've been studying for the last kind of 6 months in the column density, so like the observed density of these highly magnetized supersonic turbulence simulations that I've been playing with. So actually this in the background is actually the 10,048 cubed supersonic simulation that my supervisor, Christoph, has been playing with for the last couple of years. Unfortunately, I won't be talking about this, but I am part of this project, and this is a really exciting simulation. Hopefully we'll show you some results next year. Yeah, so I can't remember, someone on Tuesday said they got here from Boston on a kind of like sled with all these dogs. So I came here obviously on a kangaroo because I'm from Australia. And I really did. I mean, this is the flight that I took, this Qantas with the kangaroo in the back. Yeah, so it's very nice being here. Thanks so much for the organizers too. By the way, Australia's on fire at the moment. It's not so nice. So these are things I've been working on this year. I've kind of been playing a lot with these space filling factors, so fractal dimensions you could call them, as a function of length scale in your turbulence. So you can kind of start really small scales in your turbulence. So like things like when you're on this filament and you can expand out and the kind of space filling factor really changes. So that was some interesting stuff. But yeah, really this talk is going to be focusing on this paper that just got accepted on Friday, I think, last Friday. These like filaments and striations, these anisotropies that we find in MHD turbulence. And also this really interesting project reconstructing the 3D density distribution from the projected distribution. So really, I'm going to be talking about these two things. And overall, I mean, I've been looking at density structures in supersonic turbulence. So let me just kind of set the scene. Blakesley kind of did this on Monday a little bit, and there'll be a bit of overlap with what I'm going to say. But this is the kind of spaces and length scales that I live at. So this is an extremely intuitive number, 10 to the 18 centimeters, so no jargon here at all. And on time scales of like 1 million years, so quite large time scales, quite large length scales. Actually, not if you do galactic stuff, of course, very small. But these clouds are typically, like Mach 10, so very supersonic, and they do have dynamically relevant magnetic fields. So kind of like the first order approximation to these clouds, which was part of the discussion, I think maybe on Wednesday or Tuesday, is that these are kind of like isothermal equation states, supersonic compressible MHD with stochastic driving. There's no gravity here. Sorry about that. But yeah, so these are my spherical cows. And what does our spherical cow look like as a distribution? So this is a beautiful molecular cloud. Looks wonderful. This is what it looks like to a theorist. Essentially, you just have this log normal distribution in densities, and all the stuff that can form stars is like at this side of the distribution. So what does that stuff look like? So it looks like this really high density filamentary shock kind of structure. And you can see I'm going all the way up to Mach 100 here. So you get so many shocks and filaments in these really high Mach limits. And we see that essentially stars form in junctions of these kind of filamentary and shocks. So these interacting filaments and shocks, they form the right conditions, these really high density regions in the cloud, and stars will form in these with some efficiency. Essentially, as Blakesley said at the start of the week, you can kind of wind up this Mach number, and as you wind up the Mach number, you can really see this this regulation process. The regulation process and how turbulence really regulates the star formation rate is essentially it sets the width of this distribution, but it also moves the critical density across at the same time. So it's kind of a battle between the width of the distribution and also this critical density. And this critical density is some function of like the magnetic fields, the Mach number, and the gravity, and then the dispersion itself, the density, the variance of that distribution is also set by the Mach number, the type of driving that you do, and also the magnetic fields. So this is where we play in star formation at the molecular cloud level. So you can see in these equations how you actually calculate the star formation rate. They rely on the 3D density, but we only really observe the projected density. So these 3D density statistics are highly important, and we want to try to map the essentially projected density statistics, the density statistics of the column density to these 3D statistics. So what does that look like? Just to remind you what these kind of, there's my spherical cow, by the way, it's definitely a cubic cow. But yes, so we have here the projection, we have here the projection, this is the column density. Down here, this is our line of sight as an observer. And I'm just showing down the bottom here the distributions at different, essentially Mach numbers and alpha Mach numbers. You see these are two different distributions. These are quite different things. So how might we do that? Well, we can start with some really cool relations in the power spectrum. So essentially, if you integrate over the power spectrum of a periodic field with a mean of 0, you're going to get back the variance. So in that first mode, that contains the mean. When you take out your mean off your field, you remove the first mode of the power spectrum, and the rest of the power spectrum is just the smeared variance over all scales. So we can integrate this guy, and we just get back the variance, the dispersion. You can also show that essentially the Fourier transform of the column density is kind of proportional to a Fourier transform of a slice of the real density. And so you kind of reduce it to this kind of problem where you want to integrate over the 3D power spectrum of your cloud. This is the thing that's important. We want to get this dispersion. And we turn this into a problem of integrating over the column density power spectrum multiplied by some factor. But we don't know what this factor is. Well, we do know what it is actually for an isotropic cloud. It ends up being this really simple kind of, you take the column density power spectrum and you kind of rotate it in 3 dimensions, and then you'll get out the this velocity dispersion. So I hope that makes sense. But in MHD turbulence, which I said to first approximation are our molecular clouds, we have these eddies that are highly elongated along the mean magnetic field. At least that's what we think. So we have this anisotropy kind of built into MHD. So we have to deal with this anisotropy. We can't use this isotropic approximation and think that we can still construct these density dispersions properly. So how do we explore this kind of anisotropy? Well, this is the thing that I've been playing with. So these are my 20 simulations from essentially very supersonic Mach numbers down the bottom here. This is all Mach 20. And then very subalphanic turbulence. So this is all in the subalphanic regime, Mach alpha 0.01. So this is like a beta range from like 50 to 5 times 10 to the negative 5. So a large range of different parameters here. And these are 10 turnover times, essentially. So here up here, you can see some extremely anisotropic behaviors. So you see these beautiful kind of striations appearing, all these striations that run up along the magnetic field. And then down here in the high Mach number case, subalphanic still, you see all these perpendicular shocks running across the magnetic field. And I mean, there's lots of statistics that we can take from this. These are the first 4 moments of the distributions. And I just wanted to show you this really quickly, just to show you how different these distributions are. You know, there's not even a constant scaling between the 2 variances of the distribution. You see these differences here aren't scaling the same way across the distribution. So there's not like a constant factor between the variance even. But yeah, these distributions are very, very different. Okay, so now I'll take you to this kind of just exploring the anisotropy in these 20 distributions, these 20 simulations, which is what we have to do first. If you want to do these reconstructions, then we have to explore. Yes, Lexi. 20.
Do you really trust that you're capturing all the fluctuations at Mach 20 in terms of the variance? I think there was a study by Dan Price and Christoph where they were saying that they weren't able to capture the variance at those Mach.
So why would that be?
Numerical effect.
Oh, okay. Okay. Yeah, possibly. I'm not too sure. I haven't looked into it.
Do you actually believe that?
Yeah, that is a good question. I'm not sure. So let's, anyway, play with the power spectrum. So the power spectrum is an interesting quantity, the power spectrum of the column density. And this is what an isotropic power spectrum looks like, by the way. So here we have our scales that are perpendicular to the magnetic field, and here we have our scales that are parallel to the magnetic field. And you see this has perfect rotational invariance. This is an isotropic power spectrum. So this is for the case when the magnetic field is really weak, Mach alpha 10. And there's some really cool parallels here with Starry Night. I think Blakesley pointed this out at the start of the talks again. So you can take Starry Night, you can reduce it into its channels, you can look at the power spectrum of these channels, and you see also Van Gogh liked to paint these isotropic things as well. He wasn't so good at large scales, painting large scale isotropic, but very good at small scale isotropic things. Yeah. And by the way, this is Van Gogh with the actual supersonic simulation imposed in the background that I did the other day. Yeah, anyway, so we can measure the anisotropy very easily here. We can kind of get this anisotropy factor. We can fit all these like circles on the isocontours, and we can just measure the ratio between these axes, and you can get an anisotropy factor out here. And I thought this was probably interesting for you, Boris, because here I'm just using spectral amplitudes. There's no kind of scaling. There's no kind of slopes here. So this is what you were talking about yesterday. We should be using spectral amplitudes for anisotropy. Here it is. So we can do that for all of our simulations. We can average over a number of turnover times, and we get these really interesting structures here. So essentially, the anisotropy only really comes in the subalphanic regime, and you get these 2 distinct modes. You get anisotropies kind of along K perp, and you get anisotropies along K parallel. So what do these correspond to? Well, you can, now that we have these fits, we can just extract these anisotropies essentially immediately in K space, and then put it back into real space, and we kind of see what they are. So this guy corresponds with all these striations that go up in real space, and this guy corresponds to all these perpendicular filaments across the magnetic fields. So that's the key, this bimodal anisotropy in the column density. The whole idea behind these things is that you essentially have these magnetosonic fast waves that travel through the fluctuating magnetic fields, and they create these like overdensities that run parallel with the magnetic fields. but then you also have this hydrodynamical flow that's flowing really fast up the fields and creating these really strong perpendicular shocks. And we can actually see that, so we can take our simulations, draw a bunch of velocity streamlines. Here I've convolved the streamlines with the divergence of the flow. And you see all this hydrodynamical flow flying up the streamlines, creating these extremely divergent, negative divergent structures, these hydrodynamical shocks. And you also see this kind of transient magnetosonic wave moving through the flow like this big structure here. Very cool. I like that picture. So this anisotropy is really quite, as you expect, it's really quite complicated. It's a scale-dependent anisotropy, which we see in MHD, in the energy spectrum as well. And so we do some averaging over the scales, and you can get some interesting relations. So essentially, as we saw in the 2D case, the alpha Mach number kind of controls the anisotropy, so whether it's on or off. So as you go to very low alpha Mach number, you have anisotropy. As you go to really high alpha Mach number, you have no anisotropy. So it's perfectly isotropic along this line. And then essentially, like in the Mach number, the Mach number kind of controls this kind of power law that the anisotropy has. So if you have a power law of 0 here, the constant, you're completely isotropic. But as you ramp up the Mach number, what happens is this power law kind of steepens. So very interesting. So I guess just to summarize, these kinds of anisotropies are associated with these magnetosonic waves that we see in the column density of the MHD turbulence. And these kind of anisotropies, and we're not too sure why, but it seems like Mach 4 is kind of this critical transition. I'm not too sure why at all. But you see the contours have these kind of lack of diagonal modes. All they are full of is these striations and these shocks. But here you get something much smoother. So this Mach 4 is kind of the transition between these two different modes of anisotropy in the column density. We can just kind of do a hand-wavy application here. So BRIC is this CMZ cloud, which Christoph, my supervisor, studied in 2016. He did this very thorough analysis of it. You have the mean field components here in red. You have these filaments that he's identified here. And you have the power spectrum over there. So based on just, a kind of hand-wavy kind of application of just looking at our power spectrums and looking at this power spectrum, we would kind of predict that it's a highly supersonic cloud and that it has some kind of subalphanic turbulent regime as well. And indeed, if we measure it based upon these quantities in the 2016 paper, it's Mach 11 and Mach alpha 0.3. So it seems just to qualitatively agree. So I guess I'll leave you with this slide now. So yeah, I won't read it out. It's all there. Cheers.
Yeah, Mordecai.
Hi.
So I have two questions about the application to observation.
Okay, yeah.
Gravity and viewing angle.
Yes.
So real observed clouds are, except if you go to the very fluffiest little things like Pipe Nebula, they're self-gravitating.
Yes.
And that produces its own filamentary and anisotropic structure.
Yes, agreed.
And also the angle with the mean magnetic field.
Yes.
Got it. Good.
So this is what happens with the angle of the mean magnetic field. Essentially, as you're facing the field, as the field's coming straight at you, you have an isotropic power spectrum. When it's facing side on, you have the strongest anisotropy. And I agree, yeah, these things are definitely degenerate here, and it's hard to tell. I mean, this was more of a sanity check than, I'm not trying to measure these numbers at the moment. It's just a sanity check. Yeah.
Okay, yes.
I noticed you had scaling behaviors where the exponent apparently depended continuously on
The alpha.
on Mach number.
Yeah.
Should I really view those as asymptotic scaling regimes where there is a continuously varying exponent, or are you seeing a crossover from one regime to another and you're subasymptotic, so we don't really know?
Yeah, I'm really not too sure. So this is a bit of mystery at the moment, this kind of scaling relation. So it's something that we want to explore in the future, but yeah, I'm really not too sure.
Okay, any other question? Okay, so I have a question that when you have really low alpha Mach number and you have a large range of scales where the turbulence is weak, and then the anisotropy is different from GS95 scaling. And did you see that, or did you?
Oh, so this is all in the density structures. So
Okay.
the Goldrich-Shadar is all about the energy spectrum. So I mean, we get nothing like GS195. I mean, these are the kind of scale-dependent anisotropies that we find. I mean, this is exactly the opposite. Essentially, in the very high Mach number case, you get the wrong power law.
In principle, you have it, but you're looking at density.
Yeah.
So that suggests that the striations that we see in clouds, this result suggests it's in the weak turbulence regime that you think?
Yes, yeah. So less than Mach 4.
Okay. Any other question? No. Okay. Let's thank James again. Is this the last?